And now in this lecture we'll answer on two questions. In the first question we'll find out the radius of this circle that is inscribed by triangle ABC, and in the second question we'll find out the area of this rectangle ABCD that blocks this circle. So we'll start with the first method. We'll start with the first question, and we'll do the first question in two different methods. So we'll start with the first method. But before that, of course, I will present to you the question itself. In the drawing, we have triangle ABC, side BC equals to 2 units, angle ABC equals to 60 degrees, angle ACB equals to 75 degrees, and our mission is to find out the radius of this circle that is inscribed by triangle ABC, this triangle ABC. So we start with the first method. From point C we go perpendicular on AB. This angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AB as D. In the next step, I'll copy the right green triangle DBC in a new page, and we'll analyze triangle DBC. So this is the triangle DBC, angle BDC equals to 90 degrees. Angle DBC equals to 60 degrees. And side BC equals to 2 units. So this is the right triangle DBC that I copied from the original drawing. The sum of the angles in triangle DBC must be equal to 180 degrees. So which angles here in triangle DBC? We have this angle that is equal to 90 degrees, plus this angle that is equal to 60 degrees, plus the missing angle that we define as angle X. In total, the sum of those three angles must be equal to 180 degrees, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. Here 90 degrees plus 60 degrees is 150 degrees, plus X equals to 180 degrees. Here we subtract 150 degrees from this equation, and we get that angle X equals to 180 degrees minus 150 degrees, it is equal to 30 degrees. So here the missing angle X is equal to 30 degrees in its size. Write it down. We'll continue to focus on the right triangle DBC. In the right triangle DBC, It is very easy to see from the drawing that sinus 30 degrees equals to dB over BC. Sinus 30 degrees is 1/2, so let's substitute sinus 30 degrees by 1/2, and it is equal to dB over BC, but BC equals to 2 units, therefore we substitute BC by 2. Here we multiply this equation by 2, and we get that dB equals to 1 unit. dB equals to 1 unit. Here dB equals to 1 unit. We'll continue to focus on the right triangle, triangle DBC. In the right triangle, triangle DBC, cosine 30 degrees is equal to DC over BC. So cosine 30 degrees equals to DC over BC. BC is 2, so we substitute BC by 2. So here cosine 30 degrees is square root of 3 over 2, and it is equal to DC over 2. We will multiply this equation by 2, and we will get that DC equals to square root of 3 units. DC equals to square root of 3 units. Here DC equals to square root of 3 units. What is the size of angle ADC? What is the size of this angle, angle ADC? From the drawing it is very easy to see that the size of this angle, angle ADC, equals to the size of the big angle, that is angle ACB, minus the size of the small angle, angle DCB. Again, ACB minus DCB equals to the size of this angle. Angle ACB equals to 75 degrees. Angle DCB equals to 30 degrees according to what we have already found out. So 75 degrees minus 30 degrees equals to 45 degrees. In the next step, I will copy the right triangle, triangle ADC in the new page, and we will analyze triangle ADC. Angle ADC equals to 90 degrees. Sine DC equals to square root of 3 units. Angle ACD equals to 45 degrees. This is the right triangle, triangle ADC that I copied from the original drawing. The sum of the angles in triangle ADC equals to 180 degrees. So which angles we have in triangle ADC? We have this angle that is equal to 90 degrees, plus this angle that is equal to 45 degrees, plus this angle that we'll define as x. In total, the sum of those three angles must be equal to 180 degrees. 90 degrees plus 45 degrees is 135 degrees, plus x. In total, it must be equal to 180 degrees. Here we subtract 135 degrees from this equation, and we get that the missing angle, angle x, equals to 180 degrees minus 135 degrees, it is equal to 45 degrees. So we found out that here angle X equals to 45 degrees. We continue to focus on the right triangle, triangle ADC. In the right triangle, triangle ADC, those two angles are equal to each other. And we have the rule that in front of equal angles in the triangle, there are equal sides. In front of this angle, we have side DC. In front of this angle, we have side AD, and those two sides must be equal to each other because they are located in front of equal angles. So DC equals to AD, but we have only found out that DC equals to square root of 3 units. So from this equation, square root of 3 equals to DC equals to AD, we derive that AD is also equals to square root of 3 units. AD equals to square root of 3 units. So here AD equals to square root of 3 units. We continue to focus on the right triangle, triangle ADC. We'll implement the Pythagoras theorem on the right triangle ADC in order to find out the size of the length of the hypotenuse. According to the Pythagoras theorem, by PT is the abbreviation for Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is AC, therefore the square of the hypotenuse is AC squared. It must be equal to the sum of the squares of the perpendiculars, that is to say it must be equal to AD squared plus DC squared. So here AC squared equals to AD square. AD is square root of 3, so AD square is square root of 3 square, that is 3. Plus DC square. DC is square root of 3, so DC square is square root of 3 square, that is also 3. So in conclusion, we found out that AC square equals to 3 plus 3, that is 6. We take out of this equation and we get that AC equals to the square root of 6 units. AC equals to the square root of 6 units. So I feel that AC equals to square root of 6 units. In the next step, I present to you a new formula that will help us to find out the radius of this circle that is inscribed by a triangle ABC. So, we actually have here a circle with radius R that is inscribed by a triangle ABC that could be any triangle. According to the new formula, the radius of this circle that is inscribed by triangle ABC is equal to the area of triangle ABC that blocks the circle over the semi-perimeter of triangle ABC. What is the semi-perimeter of triangle ABC? It is equal to the perimeter over 2. That is to say, it is equal to the sum of the lengths of the sides, that is A plus B plus C over 2. Okay, so we use this formula in order to find out the radius of our circle. That is the radius that we are looking for. Okay, so here the radius of this circle that is inscribed by triangle ABC is equal to the area of triangle ABC over the semi-perimeter of triangle ABC. So, what is the area of triangle ABC? The area of triangle ABC is equal to the base of the triangle times the height to the base over 2. the base times the height over 2. So the area of triangle ABC equals to the base. We take the base as side AB. The height to the base is side CD because it makes 90 degrees with the base. So it is DC over 2. So AB times DC over 2 is the area of ABC. What is the length of side AB? The length is 1 plus square root of 3 times DC. DC is square root of 3 over 2. So in conclusion, we found out that the area of triangle ABC equals to the value of this expression, and the value of this expression equals to 2.366 square units. Okay, we found the area of triangle ABC. In the next step we find out the semi-perimeter of triangle ABC, which is equal to the perimeter over 2. So the semi-perimeter of triangle ABC equals to the perimeter, that is AB plus AC plus BC, and if we divide the perimeter by 2 we get the semi-perimeter. AB equals to 1 plus square root of 3 units, AC equals to square root of 6 units, and BC equals to 2. If we divide it by 2 we get the semi-perimeter. So here S, actually the value of this expression is equal to 3.59 units. So the radius of the circle is equal to the area of triangle ABC over the semi-perimeter of triangle ABC. The area of triangle ABC is 2.366 and the semi-perimeter of triangle ABC is 3.59 units, and if we divide the two numbers together we get that the radius of the circle that we are looking for is equal to 0.6589 units. Okay, the radius of this circle is equal to 0.6589 units. We finished the first method. In the next step I present to you the second method. In the second method, we'll define the center of the circle as point O. We define the point of tendency of tangent BC in this circle as point D. We define the point of tendency of tangent AC in this circle as point E, and we define the point of tendency of tangent AB with this circle as point F. We join points O and D together by a straight line. Point O is the center of the circle. Point D is the point of the circle itself, therefore OD is the radius of the circle that we will define as R. According to rule number 1, the radius is drawn to the point of tendency, therefore this angle equals to 90 degrees and this angle also equals to 90 degrees. We join points O and F together by a straight line, O and D together by a straight line. Point O is the center of the circle, point E is the point of the circle itself, therefore O is the radius of the circle that is equal to R. Again, here we have the radius OE that is drawn to the point of tendency, therefore This angle will be equal to 90 degrees, and this angle also will be equal to 90 degrees according to rule number 1. We join points O and F together by a straight line. Point O is the center of the circle, point F is the point of the circle itself, therefore OF is the radius of the circle, that is equal to R. The radius OF is drawn to the point of tendency, therefore this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule number 1. We join points B and O together by a straight line. And we join points O and C together by a straight line. In the next step, I will present to you rule number 2. According to rule number 2, the lengths of two tangents from a common external point to a circle are equal. Here we have the common external point P. From the common external point P, we have tangent PA and tangent PB to this circle. And according to rule number 2, the lengths of those two tangents are equal to each other. That is to say, PA equals to PB. We can implement rule number 2 in our drawing, because in our drawing we have the common external point B. From the common external point B, we have tangent BF, and we also have tangent BD. And according to rule number 2, the lengths of those two tangents are equal to each other. That is to say, BF equals to BD. Likewise, we have the common external point C. From the common external point C, we have two tangents to the circle, tangent DC and tangent CE. And according to rule number 2, those two tangents are equal to each other. That is to say, CE equals to DC. Okay, so in the next step, we prove that the green right triangle ODB is congruent to the orange right triangle OBF. Why those two triangles congruent to each other? So write it down. Yeah. The green triangle is triangle ODB, and is congruent to the orange triangle FOB. So why those two triangles congruent to each other? First of all, we just right now found out that FB equals to BD, according to rule number 2, FB equals to BD. In addition, FO equals to OD. They are both the radii of the circle, that is equal to R, therefore they are equal to each other. And finally, OB is the common side that belongs to both triangles, so OB equals to itself. It's the common side that belongs to both triangles. We actually found out that the orange triangle BOF can go into the green triangle OBD according to side rule. I write it down. Triangle OBD can go into triangle FOB according to side rule. And from the fact that the green triangles can go into the orange triangle, we conclude that those two angles are equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. So here, if we define this angle as alpha, so here those two angles are equal to each other, it means that angle OBF, this angle, is equal to this angle, that is actually angle OBD. Angle OBF equals to angle OBD according to the rule that corresponding angles in congruent triangles are equal to each other. So if we define angle OBF, this angle, as alpha, then from this equation alpha equals to OBD equals to OBF, we derive that angle OBD is also equals to alpha. Angle OBD is also equals to alpha. Therefore, we actually found out that both those two angles are equal to alpha. And the sum of those two angles is alpha plus alpha, and alpha plus alpha must be equal to 60 degrees according to what is given as the equation. We can write down that alpha plus alpha equals to 60 degrees. Alpha plus alpha is 2 alpha, that must be equal to 60 degrees. We divide this equation by 2, and we get that alpha equals to 30 degrees. So here, this angle is angle alpha that is equal to 30 degrees, and this angle, it is also angle alpha that is also equals to 30 degrees. Okay, and here it is very easy to prove that those two angles, those two triangles also can go into each other according to side rule, and from the fact that those two triangles can go into each other, we conclude that those two angles equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. So here we can write down that this angle, this is actually angle ECO, is equal to this angle, this is actually angle OCD. Those two angles are equal to each other according to the rule that corresponding angles in congruent triangles are equal to each other. So if we define angle ECO as theta, then angle OCD must be equal to theta also. So those two angles, they are both equal to theta, and according to what is given as the question, the sum of those two angles, that is theta plus theta, equals to 75 degrees. Theta plus theta is 2 theta, and 2 theta equals to 75 degrees. We divide this equation by 2, and we get that theta equals to 37.5 degrees. Angle theta equals to 37.5 degrees. Okay, so in the next step, we focus on the green triangle OBD. In the green triangle OBD, it is very easy to see that tangent 30 degrees is equal to OD over BD. I repeat again, the green triangle OBD times 30 degrees equals to OD over BD. Okay? But here OD equals to R, so we substitute OD by R over BD. So we found out that tangent 30 degrees equals to R over BD. We will multiply this equation by BD and then we divide it by tangent 30 degrees and we will get that BD equals to R over tangent 30 degrees. Okay. In the next step, we will focus on the yellow right triangle, triangle ODC. In the yellow right triangle, triangle ODC, it is very easy to see from the drawing the tangent is 37.5 degrees. Is equal to OD over DC. Tangent 37.5 degrees equals to OD over DC. OD equals to R, so we substitute OD by R over DC. Here we found out that tangent 35 degrees equals to R over DC. We will multiply this equation by DC and then we divide it by times 37.5 degrees and we will get that the value of DC is equal to R over tangent 37.5 degrees. So we actually found out the values of DC and the value of BD. Okay. So here, and what is the value of BC? It is very easy to see from the drawing that BC equals to BD plus DC. Here, BC equals to BD plus DC. I'll do it again. BC equals to BD plus DC. Okay. So BC equals to BD, that is actually equals to R over tangent 30 degrees according to what we have already found out, plus DC, that is equal to R over tangent 37.5 degrees according to what we have already found out. So here we take R as a common factor out of those two expressions. R is a common factor. What is left from R over tangent 30 degrees after we took from it R as a common factor? What is left is actually 1 over tangent 30 degrees. And what is left from R over tangent 37.5 degrees after we took from it R as a common factor? What is left is actually 1 over tangent 37.5 degrees. Okay. So it is R times 1 over tangent 30 degrees. It is actually equals to 1.732 plus 1 over tangent 37.5 degrees. It is equal to 1.303. And here 1.732 plus 1.303 equals to 3.035. So in conclusion, we found out that BC equals to R over R times 3.035. BC equals to 2, so we substitute BC by 2, so 2 equals to R times 3.035. We divide this equation by 3.035 units, and we get that R equals to 2 over 3.035, and 2 over 3.035 is equal to 0.6589 units. So if in both methods you arrive to the same result, that the radius of the circle that is described by triangle ABC equals to 0.6589 units. So in the next step I present to you the second question, and we solve the second question in two different methods. In the problem we have rectangle ABCD. Inside rectangle ABCD we have this circle that is described by rectangle ABCD. Chord SP equals to 6 units, line segment QS equals to 5 units, and our mission is to find out the area of this rectangle ABCD. So first of all, we will define the center of the circle as O. We will define side AB as A. We define side BC, the width of rectangle ABCD as B. BC is also the diameter of the circle, so I write it down, is equal to the diameter of the circle. We know that all the angles inside the rectangle are right angles, so this angle equals to 90 degrees. This angle is also equals to 90 degrees. This angle equals to 90 degrees. And finally, this angle is also equals to 90 degrees. I present to you rule number 4, and we will implement rule number 4 in our drawing. According to rule number 4, the perpendicular from the center of a circle to a chord bisects the chord. O is the center of the circle, the perpendicular from the center of the circle is OM, and the chord is CD. So the perpendicular OM, according to rule number 4, bisects chord CD. That is to say, CM equals to MD. Again, the perpendicular OM from the center bisects chord CD, that is to say CM equals to MD. We can implement rule number 4 in our drawing, because in our drawing we will draw perpendicular from point O to chord SP. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O to chord SP as M. According to rule number 4, the perpendicular OM from the center, that is O, bisects chord SP. That is to say, SM equals to MP. So if we define MP as X, Then from this equation Sm equals to Mp equals to x, we derive that Sm is also equals to x. Here Sm equals to x. So we actually know that Sp equals to Sm plus Mp, that is to say Sp equals to Sm, that is x, plus Mp, that is also x. That is to say Sp equals to x plus x. Sp equals to x plus x is 2x, 2x equals to Sp. It is given us an equation that Sp equals to 6. So from this equation 6 equals to Sp equals to 2x, we derive that 2x is also, we derive that 2x equals to 6. We divide this equation by 2 and we get that x equals to 6 over 2, that is 3. Here x equals to 3 units and here x equals to 3 units. Okay. In the next step, we join points O and P together by a straight line. Point O is the center of the circle, point P is the point of the circle itself, therefore OP is the radius of the circle that we will define as R. According to what we have already found out, we have already found out that the diameter of the circle equals to B. So if the diameter of the circle equals to B, the radius must be equal to half of it, that is to say the radius of the circle must be equal to B over 2. Okay. Here we have the radius OP, that is 1 to the 4th of tendency, therefore this angle will be equal to 90 degrees and this angle will be also equal to 90 degrees according to rule number 1, that the tangent to a circle is perpendicular to the radius to 1 to its point of tendency. We define the point of tendency of tangent DC with this circle as point F. We join points O and F together by a straight line. Point O is the center of the circle, point F is the point of the circle itself, therefore OF is the radius of the circle, that is equal to R. Here we have the radius OF that is 1 to the point of tendency, therefore according to rule number 1, this angle equals to 90 degrees and this angle also equals to 90 degrees. In quadrilateral OPFC, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees in order to complete the sum of the angles in quadrilateral OPFC to 360 degrees. This angle must be equal to 90 degrees. Therefore, actually, quadrilateral OPFC that has 4 right angles, it must be at least a rectangle, if not a square. So here, from point O, we will draw perpendicular on BC. Again, from point Q actually, we will draw perpendicular on side BC of rectangle ABCD. So here this angle equals to 90 degrees and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point Q and BC as T. We define the intersection point between QT and QF as L. So inside quadrilateral QPLT, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. So I already explained before. So actually, inside quadrilateral OPLT, we have 4 right angles, and any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we will relate to quadrilateral OPLT LT is a rectangle. Why? Because it has 4 right angles. Repeat again. Quadrilateral OPLT is a rectangle. And we know that the opposite sides of a rectangle are parallel to each other. That is to say, side OP must be parallel to side LT. OP is parallel to LT. Okay. Repeat again. Side OP is parallel to side LT in rectangle OPLT. According to the rule that the opposite sides of a rectangle are parallel to each other. But here, side LT is part of the perpendicular QT. Okay, and QT is a perpendicular, it is absolutely a straight line. I write it down. QT is a straight line because of the fact that it is a perpendicular. QT is a straight line. And LT is part of the straight line QT. And LT is parallel to OP. So if part of the straight line QT is parallel to OP, the straight line QT itself must be also parallel to OP. Okay? Why? Because if part of a straight line is parallel to another straight line, then the straight line itself must be also parallel to the other straight line. Therefore, QT is parallel to OP. QT is parallel to OP. QT is parallel to OP. And here we have rule number 9. According to rule number 9, alternating angles between parallel lines are equal to each other. Line A is parallel to line B, therefore those two pink angles that are defined as alternating angles, they are equal to each other. According to this rule, rule number 9. We can implement rule number 9 in our drawing, because in our drawing, OP is parallel to QT, and those two angles are defined as alternating angles that are located between the parallel lines OP and QT, therefore they are equal to each other. So I write it down. Here, angle OPQ this angle is equal to this angle, that is actually angle PQT. Repeat again, angle OPQ is equal to angle PQT according to rule number 9. So if we define angle PQT as theta, here angle PQT equals to theta according to our definition, then from this equation theta equals to angle OPQ equals to angle PQT, we derive that angle PQT is also equals to theta. So here, this angle PQT equals to theta. Okay. So in the next step, we focus on quadrilateral QTDC. In quadrilateral QTDC, we have 1, 2, 3 right angles. Therefore, the fourth angle, this angle must be also equal to 90 degrees. So quadrilateral QTDC is 4 right angles. Therefore, it must be at least a rectangle, if not a square. So we relate to quadrilateral QTDC as a rectangle. I'll repeat again, quadrilateral QTDC is a rectangle. Why? Because it has 4 right angles. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, side QT must be equal to side DC. QT must be equal to DC. But we know that ABCD is a rectangle and the opposite sides of rectangle ABCD are equal to each other. That is to say, DC equals to AB. Here DC equals to AB. And from this equation QT equals to OD equals to AB, we will derive that QT equals to AB. QT equals to AB. But here, according to our definition, AB equals to A. AB equals to A. So we can write it that AB equals to A. And from this equation QT equals to AB equals to A, we will derive that QT is also equals to A. Here QT is equals to A. QT equals to A. In the next step, we'll focus on the right triangle, triangle OMP. So I'll copy the right triangle, triangle OMP in the new page and we'll analyze triangle OMP. Angle OMP equals to 90 degrees according to our construction. MP equals to 3 units. The hypotenuse OP equals to B over 2. This is the radius. Angle, this angle equals to theta. So actually, this is the right triangle, triangle OMP that I copied from the original drawing. In triangle OMP, cosine theta equals to MP over OP. Again, cosine theta equals to MP over OP. So I write it down. So MP equals to 3 units, we substitute MP by 3, and OP equals to B over 2, we substitute OP by B over 2. Here we'll move to the numerator, 2 times 3 is 6. We'll move B to the denominator, so we get there 6 over B. So in conclusion, we found out that according to equation number 1, cosine theta equals to 6 over B. In the next step, we'll focus on the right big triangle, triangle QTP. In the right big triangle, triangle QTP, it's very easy to see from the drawing. That cosine theta equals to QT over QP. Repeat again. In the right big triangle, triangle QTP, cosine theta equals to QT over QP. What is the value of QT? The value of QT is A, so we substitute QT by A over QP. What is the value of QP? QP equals to 5 plus 6, that is 11. So we substitute QP by 11. So in conclusion, we found out that according to equation number 2, cosine theta equals to A over 11. So actually you have two different expressions for cosine theta. Therefore we create equation number 3 that states that cosine theta according to equation number 1 must be equal to cosine theta according to equation number 2. So cosine theta according to equation number 1 equals to 6 over B. It must be equal to cosine theta according to equation number 2, that is equal to A over 11. So in conclusion, found out that according to equation number 3, 6 over B equals to A over 11. Here we cross multiply this equation, equation number 3, and we get that according to equation number 3, A times B equals to 6 times 11, that is 66. So AB equals to 66 according to equation number 3. And we know that the radius, the area of rectangle ABCD equals to its length times its width. The length is equal to AB and the width is equal to BC. According to our definition, AB equals to A and BC equals to B. So in conclusion, we found out that the area of rectangle ABCD equals to AB. But we just right now found out that AB equals to 66. So we can write that AB equals to 66. So in conclusion, we found out that the area of rectangle ABCD equals to 66 square units. Okay, so we finished with the first method. In the next step, I present to you the second method. The second method, we define the center of the circle as O. We know that all the angles inside a rectangle are right angles, so this angle equals to 90 degrees. This angle also equals to 90 degrees. This angle equals to 90 degrees. And this angle is also equals to 90 degrees. We define the length AB as A, and we define the width of rectangle ABCD, BC, the length BC, the width BC of rectangle ABCD as B. BC is also the diameter of the circle, so I write it down. This is the diameter of the circle. Therefore, according to our definition, the diameter of the circle equals to B. We'll join points O and P together by a straight line. O is the center of the circle. P is the point of the circle itself. Therefore, OP is the radius of the circle that we define as R. If the diameter is B equals to B, it means that the radius must be equal to half of it. That is to say, the radius of the circle will be equal to B over 2. According to rule number 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. We'll extend the radius PO until it intersects with side AD of rectangle ABCD. We define the touching point of the extended radius PO and AD as T. So in quadrilateral ABTP, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also a right angle. So quadrilateral ABTP has 4 right angles. Any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we'll relate to quadrilateral ABTP is a rectangle. And we know that the opposite sides of a rectangle are equal to each other. So AB equals to A. So therefore, side AB must be equal to side TP. But according to our definition, side AB equals to A, therefore TP must be also equal to A, because they are equal to each other. TP equals to AB. Here, in quadrilateral TPDC, we have 1, 2, 3 right angles, therefore the fourth angle must be also a right angle. It is equal to 90 degrees. What is the definition? We will define the extended radius OP and we'll define the touching point of the extended PO with the circle as point G. So we have here chord GP that passes through the center of the circle, that is point O. Therefore, chord GP is the diameter of the circle. Chord GP is the diameter of the circle, and according to what we already found out, the diameter of the circle equals to B. In the next step, we'll join points S and G together by a straight line. So here we created peripheral angle GSP, and peripheral angle GSP rests on GP, that is the diameter of the circle. And we actually have here rule number 5 that relates to a peripheral angle that rests on the diameter of the circle. Here according to rule number 5, any peripheral angle that rests on the diameter of the circle must be equal to 90 degrees. The diameter is AB, peripheral angle AMB rests on AB, that is the diameter of the circle, therefore it is equal to 90 degrees. Okay, so here we can implement rule number 5 in our drawing, because in our drawing we have peripheral angle PSG that rests on GP, that is the diameter of the circle, therefore peripheral angle PSG equals to 90 degrees according to rule number 5. In the next step, we will define this angle SP GS theta. So, in the right triangle GSP, this angle equals to theta, this angle equals to 90 degrees, therefore this angle must be equal to 90 degrees minus theta, or because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees is 180 degrees. That is the sum of the angles in any triangle. Likewise, in the big right triangle, triangle QTP, this angle equals to theta, this angle equals to 90 degrees, therefore this angle must be equal to 90 degrees minus theta. Okay, so in the next step, we'll prove that the green small right triangle, triangle GSP, is similar to the big right triangle, triangle QTP. So why those two right triangles are similar to each other? I'll write it down. The right big triangle is QTP and is similar to the right green small triangle SGP. Why those two triangles are similar to each other? First of all, those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. Here, this angle is TQP. Is equal to this angle, that is actually angle SGP. Repeat again, angle TQP equals to angle GSP, they are both equal to 90 degrees minus theta, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, therefore they are equal to each other. So this angle, angle QTP, is equal to this angle, that is actually angle GSP. Repeat again, angle QTP equals to angle GSP, they are both equal to 90 degrees, therefore they are equal to each other. And finally, we have this angle, angle theta, that is a common angle, so angle theta equals to itself. You can write down that theta equals to theta, or you can also express angle theta in two different names. You can express angle theta as angle TPQ, that is equal to itself, to angle theta itself. You can express angle theta also as angle GPS. Okay, I'll repeat again. Here, angle theta is a common angle that belongs to both triangles, so angle theta equals to itself. It's a common angle that belongs to both triangles. So actually we found out that the big right triangle is similar to the small green right triangle according to angle similarity rule. The big right triangle, triangle QTP, is similar, this is the sign of similar, to the right small green triangle, triangle SGP, according to side side wall. And for the fact that the big right triangle is similar to the green small right triangle, we conclude that the following relationship exists between their sides. We will conclude that TP of the big right triangle over SP of the small right green triangle is equal to QP of the big right triangle over GP. Repeat again, and conclude that TP over SP is equal to QP over GP. Here, TP equals to A according to what we have already found out, so we'll substitute TP by A in equation number 1. SP equals to 6 units according to what is given us in the question, so we'll substitute SP by A. And it is equal to QP. You can see here that QP equals to 5 plus 6, that is 11. So we substitute QP by 11 over GP. GP is the diameter of the circle, that is equal to B. So we substitute GP by B. So in conclusion, we found out that A over 6 equals to 11 over B. Here we cross multiply this equation, equation number 1, and we'll get that according to equation number 1, A times B equals to 11 times 6, that is 66. So AB equals to 66 according to equation number 1, and the area of rectangle ABCD is equal to the length of the rectangle that is AB times the width of the rectangle that is BC. AB equals to A and BC equals to B according to our definition. We just right now found out that AB equals to 66. So in conclusion, found out that the area of rectangle ABCD is equal to 66 square units. Okay, so finish with the second method. In the next step, I will summarize the lecture. We'll start with the first question, of course. In the drawing, we have triangle ABC, side BC equals to 2 units, angle ABC equals to 60 degrees, angle ACD equals to 75 degrees, and inside triangle ABC we have a circle. Of the circle is inscribed by triangle ABC, and our mission is to find out the radius of this circle that is inscribed by triangle ABC. So, in the first method, we did a construction. From point C we drew perpendicular on AB. This angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and AB is D. So created here the right triangle CBD. So I copied the right triangle CBD in the new page, and we analyze triangle CBD. This is the right triangle CBD that I copied from the original drawing. In the right triangle CBD, this angle equals to 90 degrees, this angle equals to 60 degrees, this is the missing angle. So 90 degrees plus 60 degrees plus the size of this angle that is x, in total they must be equal to 180 degrees according to the rule that the sum of the angles in any triangle is equal to 180 degrees. 90 degrees plus 60 degrees is 150 degrees, and 150 degrees plus x equals to 180 degrees. We subtracted 150 degrees from this equation and found out that the missing angle x equals to 180 degrees minus 150 degrees is 30 degrees. So this angle equals to 30 degrees. We continue to focus on the right triangle DBC. The right triangle DBC, sinus 30 degrees equals to DB over BC. Again, the right triangle DCB, it is actually triangle DCB. This triangle DCB, or you can write here triangle DBC, sinus 30 degrees equals to DB over BC. So sinus 30 degrees is 1/2. It is equal to DB over BC, and BC is 2, so we substitute BC by 2. So in conclusion, we found out that 1/2 equals to DB over 2. We multiplied this equation by 2, and we found out that DB equals to 1 unit. Here, DB equals to 1 unit. We continue to focus on the right triangle DBC. In the right triangle DBC, sinus 30 degrees equals to DC over BC. Cosine 30 degrees equals to DC over BC. Cosine 30 degrees equals to DC over BC. So it is equal to DC over BC, and BC is 2, so we substitute BC by 2, and we found out that cosine 30 degrees is square root of 3 over 2, and square root of 3 over 2 equals to DC over 2. We multiplied this equation by 2, and we found out that DC equals to square root of 3 units. Here, DC equals to square root of 3 units. Then, what is the size of this angle? The size of this angle equals to 75 degrees minus 30 degrees, that is 45 degrees. And I copy triangle ADC in a new page, and we analyze triangle ADC. That is triangle ADC that I copied from the original drawing. This angle equals to 45 degrees. This angle equals to 90 degrees, and this angle is equal to x. In total, the sum of those three angles must be equal to 180 degrees. 90 degrees plus 45 degrees is 135 degrees, and 135 degrees plus x must be equal to 180 degrees. We subtracted 135 degrees from this equation and found out that the missing angle x equals to 180 degrees minus 135 degrees. It is equal to 45 degrees. So this angle equals to 45 degrees. We continue to focus on the right triangle ADC, that is also an isosceles triangle. In the right triangle ADC, we have two angles that are both equal to 45 degrees, therefore they are equal to each other. And we have the rule that in front of equal angles in the triangle, there are equal sides. So in front of this angle, we have side DC. In front of this angle, we have side AD. And those two sides must be equal to each other because of the fact that they are located in front of equal angles. Okay, so AD must be equal to DC. We already found out that DC equals to square root of 3 units. So from this equation, square root of 3 equals to DC equals to AD. We will derive that AD equals to square root of 3 units. Here, AD equals to square root of 3 units. Then we implemented the Pythagoras theorem on the right in the isosceles triangle ADC. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, AC square equals to AD square plus DC square. Okay, so AC square equals to AD square. AD is square root of 3, so AD square is square root of 3 square, that is 3, plus DC square. DC square, DC is square root of 3, so DC square is square root of 3, that is 3. So in conclusion, we found out that AC square equals to 3 plus 3, that is 6. We took out of this equation and found out that AC equals to the square root of 6 units. Here, AC equals to the square root of 6 units, so we have the lengths of all the sides of triangle ABC. Therefore, we can use here a special formula in order to find out the radius of this circle that is described by triangle ABC. According to the special formula, the radius of any circle that is described by a triangle, here R is the radius of any circle that is described by a triangle. It is equal to the R of the triangle that blocks the circle or the semi-perimeter of the triangle. So what is the area of triangle ABC? The area of triangle ABC equals to the base of the triangle times the height of the triangle, the height of the base over 2. The base we took the base as AB, therefore the eye to the base is CD because it creates 90 degrees with the base, over 2. AB is 1 plus square root of 4, 1 plus square root of 3 units. This is square root of 3 units. Here, all divided by 2. The value of this expression is 2.366, so the area of triangle ABC equals to 2.366 square units. Then the semi-perimeter of any triangle equals to the perimeter over 2. The perimeter of triangle ABC is AB plus AC plus BC, and then if we divide it by 2, we get the semi-perimeter. So here, the value of this expression, AB equals to 1 plus square root of 3, AC equals to square root of 6, and BC equals to 2. And if we divide it by 2, we'll get that the value of this expression is 3.59, and R equals to the area of triangle ABC over the semi-perimeter of triangle ABC. The area of triangle ABC is 2.366, and the semi-perimeter of triangle ABC is 3.59. So in conclusion, we found out that the radius of the circle that is described by triangle ABC is equal to 0.6589 units. We finished with the first method, then I presented to you the second method. In the second method, we defined the center of the circle as point O, and here actually join points O and D together, join points O and C together, point O and D together, O and B together, and O F and F together by a straight line. Those three angles are equal to 90 degrees according to rule number 1, that the tangent to a circle is perpendicular to the radius drawn to its point of tendency. OE equals to OD equals to OF. Here O is the center of the circle and F is the point of the circle itself, therefore OF is the radius. The same thing is true for OE and OD. They are all the radii of the circle that is equal to R according to our definition. So here I presented to you rule number 2, that the lengths of two tangents from a common external point to a circle are equal. So here we have point from the external point, point B, we have tangent BF and tangent BD. Therefore the lengths of those two tangents must be equal to each other. That is to say BD equals to BF. Likewise we have the common external point, point C. From the common external point, point C, we have tangent CD and tangent CE, and according to rule number 2, they are equal to each other. This is to say CE equals to CD. Okay? So here, then if we prove that the green triangle is congruent to the orange triangle according to side rule. Why those two triangles congruent to each other? First of all, BD equals to FB according to rule number 2. DO equals to OF, they are both the radii of the circle, therefore they are equal to each other. And finally, OB is a common side that belongs to both triangles, so OB equals to itself, therefore those two triangles congruent to each other according to side rule. And from the fact that those two triangles congruent to each other, we conclude that those two angles must be equal to each other according to the rule that corresponding sides in congruent triangles are equal to each other. Those two triangles congruent to each other, therefore those two corresponding sides must, those two corresponding angles must be also equal to each other. Okay, so here angle OBF equals to angle OBD. So if we define one angle as alpha, then the other angle must be also equal to alpha. So the sum of those two angles, alpha plus alpha, is 60 degrees according to what is given as the equation. 2 alpha equals to 60 degrees. We divided this equation by 2 and found out that alpha equals to 30 degrees. Here this angle equals to 30 degrees and this angle also equals to 30 degrees. Likewise, those two triangles are also congruent to each other according to side rule. Therefore, we can conclude from it that those triangles are equal to each other. here angle ECO equals to angle OCD. So if we define one angle is theta, then the other angle must be also equal to theta. So the sum of those two angles is theta plus theta. This is 2 theta, and 2 theta equals to 75 degrees according to what is given as the equation. Okay, we divided this equation by 2 and found out that theta equals to 37.5 degrees. Then we focused on the green triangle ODC, the green triangle ODC. Triangle theta equals to OD over BD. Triangle theta equals to OD over BD. OD equals to R, we substitute OD by R over BD. So triangle 30 degrees, it is actually triangle 30 degrees. Here it is triangle 30 degrees, that is equal to R over BD. We multiplied this equation by BD and then we divided it by triangle 40 degrees and found out that BD equals to R over triangle 30 degrees. Likewise, we repeat on the same process in the right green and the right yellow triangle ODC, the right yellow triangle ODC, triangle 37.5 degrees equals to OD over DC. Again, triangle 37.5 degrees equals to OD over DC. OD equals to R, so we substitute OD by R and found out that triangle 37.5 degrees equals to R over DC. We multiplied this equation by DC and then we divided by triangle 37.5 degrees and found out that DC equals to R over triangle 37.5 degrees. Then it is very easy to see from the drawing that BC equals to BD plus DC. BC equals to BD plus DC. BD equals to R over triangle 30 degrees and DC equals to R over triangle 37.5 degrees. We took a common factor R from those two expressions. What is left from this equation after we took from it R as a common factor? What is left is 1 over triangle 30 degrees. What is left from this expression after we took from it R as a common factor? What is left is actually 1 over triangle 37.5 degrees. 1 over triangle 30 degrees equals to 1.732. 1 over triangle 37.5 degrees equals to 1.303. And 1.3732 plus 1.303 equals to 3.035. So in conclusion, found out that BC equals to R times 3.035. We divided this equation by 3.035 and found out that R equals to 2 over 3.035. 2 over 3.035 equals to the radius of the circle, that is equal to 0.6589 units. So in both methods we found out that the radius of this circle that is described by triangle ABC equals to 0.6589 units. Then I presented to you the second question. In the drawing, we have rectangle ABCD. Inside rectangle ABCD, we have this circle. Chord PS equals to 6 units. Line segment SQS equals to 5 units. And our mission is to find out the area of this rectangle ABCD. Okay, so first of all, we define the center of the circle as point O. And then I presented to you rule number 4, that if you draw from the center of the circle perpendicular to chord SP, this perpendicular OM bisects chord SP. That is to say SM equals to MP. So if MP equals to X, then SM must be also equal to X. So SM equals to X and SP equals to X, but from the drawing it is very easy to see that X plus X equals to SP. So here X plus X equals to SP, that is X plus X is 2X and 2X equals to SP, but SP equals to 6 units according to what is given as the question. So from this equation, 6 equals to SP equals to 2x, we derive that 2x equals to 6. We divide this equation by 2 and we get that x equals to 6 over 2 is 3. So x equals to 3, x equals to 3, and x equals to 3. Then, actually, we have here we joined points O and P together by a straight line. Point O is the center of the circle, point P is the point of the circle itself, therefore OP is the radius of the circle. We know that all the angles in a rectangle are right angles, so all those 4 angles are right angles. We define AB as A and BC as B. BC is also the diameter of the circle, so BC equals to B, and B is the diameter, so if the diameter is B, then the radius must be equal to B over 2. According to rule number 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. We join points O and F together by a straight line. Point O is the center of the circle, point F is the point of the circle itself, therefore OA is the radius, OF is the radius of the circle. So we have here the radius OF that is drawn to the point of tendency, therefore this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule number 1. Then from point Q we draw perpendicular on BC. We define the touching point of the perpendicular from point Q and BC as T. So here we defined the intersection point between QT and OF as L. We created here quadrilateral OPLT. Inside quadrilateral OPLT, we have 1, 2, 3 right angles. Therefore, the fourth angle must be, this angle must be also equal to 90 degrees. Therefore, inside quadrilateral OPLT, we have 4 right angles. Therefore, quadrilateral OPLT is a rectangle. Why? Because it has 4 right angles. And we know that the opposite sides of a rectangle are equal to each other. That is to say, the opposite sides of a rectangle are parallel to each other. That is to say, OP is parallel to LT. Okay, OP is parallel to LT. But LT is part of QT. And QT is a perpendicular. QT is a perpendicular. It is absolutely a straight line. So you can write down that QT is a perpendicular in a straight line. And part of the straight line QT is parallel to OP. Therefore, the straight line itself must be also parallel to OP. Because if a part of a straight line is parallel to another straight line, then the straight line itself must be also parallel to the other straight line. Therefore, QT is also parallel to OP. Here, QT is also parallel to OT. Then I presented to you rule number 9, that alternating angles between parallel lines are equal to each other. Those 2 angles are defined as alternating angles and are located between the parallel lines OP and QT, therefore they are equal to each other. That is to say, angle OPQ equals to angle PQT. So if we define angle OPQ, this angle is theta. If we define angle QPT, if we define this angle as theta, angle QPT, then from this equation theta equals to QPT equals to PQT, we define that angle PQT is also equals to theta. So this angle is also equals to theta. Okay. Then we focused on quadrilateral QTDC. In quadrilateral QTDC we have 1, 2, 3 right angles. Therefore the fourth angle must be also equal to 90 degrees. Therefore quadrilateral QTDC that has 4 right angles is a rectangle. Okay, quadrilateral QTDC is a rectangle because it has 4 right angles, and we know that the opposite sides of a rectangle are equal to each other. That is to say, side QD must be equal to side DC. QT equals to DC, but we know that ABCD is a rectangle, and the opposite sides of a rectangle are equal to each other. That is to say, side DC equals to AB. So here DC equals to AB. From this equation, QT equals to DC equals to AB. We will derive that QT is also equals to AB. Here QT is also equals to AB. But according to our definition, QT equals AB equals to A. So you can write here that AB equals to A. From this equation, QT equals to AB equals to A. We will derive that QT is also equals to A. Here QT equals to A. In the next step, we focused on the right small triangle OPM, the right green triangle OPM. So I copied the right green triangle OPM in the new page, and we analyze triangle OPM. This is the right triangle OPM that I copied from the original drawing. This is angle theta, and OP equals to B over 2, and PM equals to 3 units. So the right triangle OPM, cosine theta equals to PM over PO. So PM equals to 3 units, and OP equals to B over 2 units. Therefore, 3 over B over 2, we move 2 to the numerator, so it is 2 times 3 is 6. We move B to the denominator, so here we get B. So in conclusion, found out that cosine theta according to equation number 1 equals to 6 over B. Then we focus on the right triangle QTP, on the right big triangle QTP. Cosine theta equals to QT over QP. Again, cosine theta equals to QT over QP. Again, cosine theta equals to QT over QP. QT equals to A, so we substitute QT by A, and QP equals to 5 plus 6, that is 11. So we substitute QT by 11. So in conclusion, according to equation number 2, cosine theta equals to A over 11. So we have two different expressions for cosine theta. Therefore, we get the equation number 3 that states that cosine theta according to equation number 1 must be equal to cosine theta according to equation number 2. So cosine theta according to equation number 1 equals to 6 over B. And it must be equal to cosine theta according to equation number 2, that is A over 11. So in conclusion, found out that according to equation number 3, 6 over B equals to A over 11. Here we cross multiply this equation number 3, and found out that A times B equals to 6 times 11, that is 66. So according to equation number 3, A times B equals to 66, and we know that the area of rectangle ABCD equals to the length of the rectangle times the width of the rectangle. The length of the rectangle is AB, the width of the rectangle is BC. So AB times BC is the area of rectangle ABCD. AB is A and BC is B according to our definition. So in conclusion, found out that the area of rectangle ABCD equals to A times B. But we just right now found out that A times B equals to 66. So we can write here that AB equals to 66. And in conclusion, found out that the area of rectangle ABCD equals to 66 square units. We finish with the first method, then I presented to you how to find out the area of this rectangle ABCD according to the second method. In the second method, we define the center of the circle as point O. We join points O and P together by straight line. Point O is the center of the circle, point P is the point of the circle itself, therefore OP is the radius of the circle. And here, according to the first method, this angle equals to 90 degrees and this angle equals to 90 degrees. It is according to rule number 1. We defined AB as A, BC as B. BC is also the diameter of the circle. So here BC equals to B, but if B is the diameter of the circle, then the radius must be equal to half of it. That is to say, the radius of the circle equals to B over 2. Okay? Then we extended the radius PO until it touches the rectangle, side AD of rectangle ABCD at point T. Okay, so here, if you focus on quadrilateral ABTP, this quadrilateral, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also a right angle. So quadrilateral ABTP has 4 right angles. Therefore, it must be at least a rectangle if not a square. So we relate to quadrilateral ABTP is a rectangle. And we know that the opposite sides of a rectangle are equal to each other. Here, AB equals to A according to our definition. So the opposite sides of rectangle ABTP, they are equal to each other. That is to say, AB equals to TP. So if AB equals to TP and AB equals to A, it means that TP is also equals to A. Likewise, quadrilateral TPDC has 1, 2, 3 right angles. Again, quadrilateral TPCD is 1, 2, 3 right angles. Therefore, the fourth angle must be also a right angle. So quadrilateral TPDC is a rectangle. Okay? So actually, then we joined points S and G together by a straight line. In this way, we created peripheral angle GSP. What is the definition of chord GP? Chord GP passes through the center of the circle, that is to say from point O. Therefore, any chord that passes through the center of the circle must be the diameter of the circle. Therefore, GP is the diameter of the circle. That is equal to B according to what we already found out. So here we have peripheral angle GSP that rests on GP, that is the diameter of the circle. Therefore, here we implemented rule number 5 that says that any peripheral angle that rests on the diameter of the circle must be equal to 90 degrees. That is to say, peripheral angle GSP that rests on GP, that is the diameter of the circle, must be equal to 90 degrees. So this angle, so if you focus on the green triangle, this angle equals to 90 degrees. We define this angle as theta. Therefore, this angle must be equal to 90 degrees minus theta, because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. Okay, so in the right big triangle QTP, this angle equals to theta, this angle equals to 90 degrees. This angle must be equal to 90 degrees minus theta, according to what we explained about the green triangle. Okay, then we proved that the green triangle is similar to the right big triangle TQP. Why those two triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, therefore they are equal to each other. And finally, this angle theta is a common angle that belongs to both triangles, so this angle equals to itself. Therefore, the big triangle QTP is similar to the green triangle GSP, according to side angle similarity rule. And from the fact that those two triangles are similar to each other, we conclude that the following relationship exists between their sides. We conclude that TP over SP equals to QP over GP. Again, TP over SP equals to QP over GP. Here, TP, what is the value of TP? TP equals to A, according to what we have already found out, so we substitute TP by A. What is the value of SP? SP equals to 6 units, according to what is given as the question. What is the value of QP? QP equals to 6 plus 5, that is 11. So we substitute QP by 11. And finally, GP is the diameter of the circle that is equal to B. Therefore, we substituted GP by B. So in conclusion, found out that according to equation number 1, A over 6 equals to 11 over B. Here, equals multiply this equation number 1, and we found out that A times B equals to 11 times 6, that is 66. So according to equation number 1, A times B equals to 66. And what is the area of rectangle ABCD? The area of rectangle ABCD equals to the length of the rectangle times the width of the rectangle ABCD. The length AB is A, and the width BC is B, according to our definition. So in conclusion, we found out that the area of rectangle ABCD equals to A times B. But we just right now found out that, that according to equation number 1, A times B equals to 66. Therefore, we can write here that AB equals to 66. And finally, we found out that the area of rectangle ABCD equals to 66 per units. So in both methods, we found out that the area of rectangle ABCD, this rectangle ABCD, equals to 66 per units. And likewise, in the first question, in both methods, we found out that the radius of the circle that blocks the radius of this circle that is described by triangle ABC equals to 0.6589 units. Okay? Thank you very much.